We've done some equation solving. Before this point, when we were rearranging formulas, we did some equation solving. We've done a little bit when we were working with percents. But it was all at a pretty basic level. Now we're going to start out with linear equations and start working with equations of various types here for the next few days. We have a couple of things that we want to accomplish today. Three things, actually. The first thing we want to make sure to do is recognize what a linear equation is. Okay? There's several different types of equations, many different types of equations. We're going to focus on linear equations today. I want you to be able to recognize what linear equations are as opposed to other types. Solve linear equations. That's going to be largely just picking up with stuff that we have done before and building on that. And then we're going to solve some linear literal equations. We'll see what a literal equation is in a little bit here. So before we solve any equations, let's take a look at that first objective and see how to distinguish a linear equation from other types. Way to tell a linear equation is you look at the powers or the exponents. If there's no powers other than 1, it's linear. So for example, the one shown there on the screen, 5x plus 3 equals 4 times 2x minus 9. Well, the only two variables that make an appearance are x on the left side and x on the right side. There's no exponents, so the exponent's assumed to be 1. That's it. They're linear. There's 2 down at the bottom that are not linear. The one on the left, 5 times 2x minus 7 equals 3x squared. You got the variable x, but there's an exponent on the 2 that's not a 1. In fact, it's squared, therefore it's not linear. The one on the bottom right, square root of 3x equals 4x plus 7. There you've got the square root of 3x, and since there's a square root of a variable, that also disqualifies it. It's not linear. Incidentally, you can probably guess, but why do they call linear equations linear? When you graph them, which we're going to be doing shortly, they'll yield straight lines on the graph. The other two down at the bottom, we can graph those. Well, we could graph them if they were related to y, and they would ultimately yield a curve that is not a straight line on the graph. So, let's take a look at a couple here. First one, we want to solve that equation. Well, we really have an order of operations here to deal with. There's no exponents. There never will be as long as we're working with linear equations. So what we need to do is, we would like to, if we could work inside this parentheses and simplify it, we would do that. But can we combine 2x plus 6? No, so there's nothing to do in parentheses. Same thing here, 6x plus 2, there's nothing to do there. We can't combine them. So there's no exponents. We can't do anything in parentheses. We move on to the multiplication, which ultimately means we're going to take that 5 and distribute it. So we have 10x plus 30 equals 24x plus 8 plus 1. Now, we've done some equation solving, and we've always made this a point. If you want to solve for x, what do you got to do with all your terms involving x? Get them together, collect them on one side. Now, you've got a choice here. You can move that 24x to the left, or you can move the 10x to the right. Which way is going to be a little bit easier? Move the 10x to the right, because when you do that, you'll be left with positive coefficients, and that tends to leave fewer mistakes. So let's move that 10x to the right. So we have 30 equals 14x plus 8 plus 1, we can call that 9. Well, along with collecting all the x terms together, we want to get anything that doesn't involve an x out of there. So we're going to have to move the move the 9 over to the left. And we're left with 21 equals 14x. And finally, get x by itself. We're going to divide both sides by 14 and reduce. So we're left with x equals 21 over 14, which is true, but that's a fraction. You can reduce that down to 3/2, or 1.5, or 1.5. Oops. Now you generally want to, when you're working with equations, you usually want to leave your answer as a fraction. Why do you want to leave it as a fraction? Usually, as opposed to just converting it to a decimal. True. If we were going to graph it, there would be an advantage to leaving it as a fraction. I hadn't thought about that, but that's true. Fractions are always exact. If you convert to a decimal, you'll often be rounding. Now, in this case, 1.5 is exactly 1.5. It's no problem. But if, for example, this were something like 7 over 3, that would be a decimal that doesn't work out evenly, and you'd have to round. Now you're compromising the accuracy of your answer, so you'd leave it as a fraction. So if it works out exact, no problem converting it. If it doesn't work out exact, leave it as a fraction. Okay. It's a little bit small. I'll write that one on the board. We want to solve this equation. Only in algebra books will you ever find these nice little equations with whole exact numbers. When you actually start using algebra, you're always going to have these decimal values. The only real issue here is how to handle the sig digs. Well, when you're doing the algebra, you always just leave plenty of decimal places, because then when you're done, you'll cut it back. Now, if you look at all these values, how many sig digs are you going to be limited to in the end? 2. But we don't know where those 2 are going to occur. In other words, those 2 sig digs might occur in the thousandths or the 10,000th spot. You could have a lot of decimal places and still only 2 sig digs. So the point is, always be generous when leaving significant digits. If you can leave them all, leave them and then round off at the end. So let's work through this one and I'll clarify what I mean by that. First of all, process similar to last one. We need to, first of all, we're going to distribute first. As of now, there's no ends that we can collect because we'd have to work inside the parentheses. But once we distribute, we'll have all kinds of them to collect. So let's distribute. 4.5 times 1.2 is 5.4n. Minus 29.25 plus 9.6 times 8.42n, 80.832. (9.6 plus 2.7). All right, now we can go ahead and collect our n terms together. Let's just work on the left side to collapse this a little bit. 5.4n plus 80.832n. (86.232). We'll leave them all there. Minus 29.25 plus 25.92 is negative 3.33. I think. That takes care of the left side, and that's still equal to 9.9n on the right. Look it up to there. Okay, again, we haven't rounded at all. I haven't rounded at all. As long as your decimals don't fill your whole calculator screen or go 6 or 8 spots, just leave them all. Then there's no rounding error. We'll round at the end. Okay. So Let's finish this up. We better shuffle that 86.232n over to the left, from the left to the right, excuse me. So we have negative 3.33 equals negative 76.332 n. Finally, we'll divide that off. And now, this is the last step. Now we can cut our answer off at, I think we said it before, how many sig digs? 2. So n is going to be equal to what does that work out to here? 0.044. There's our 2 sig digs. We're done. Okay. Well, now we're going to look at some fractional equations. You can have linear equations that involve fractions, certainly. We're going to have, in a few weeks, we're going to deal with fractional equations where your variable is in the denominator. Right now, we're not going to do that. But when you're dealing with linear fractions, as we've done in a couple of cases with other problems, you clear your fractions by multiplying everything by your LCD. Okay, well, let's take a look at one here. Let's do one that involves fractions. Let's solve this. Ask yourself, first of all, is that linear? Because a lot of fractional equations are not linear, and so you got to discipline your mind to say, all right, is that thing linear? Right now it doesn't seem important, but later on it will be important to recognize linear equations. Does that meet the criteria of a linear equation? It does. All the powers of x are 1. Also, later on we'll have equations where the x is in the denominator. And x is in the denominator, even though they have a power of 1, would actually be considered powers of negative 1 because you'd move them up to the top, and so they would not be linear. But let's solve this. Okay. Well, here's a tip for you. A lot of mistakes in linear equations in general, especially those involving fractions, particularly those involving fractions, is what to do with this negative sign that hangs out in front of a fraction. There's different ways to handle it, but what I recommend is do this. Anytime you see a negative sign hanging out in front of a fraction, move it and associate it with the top value. Then it's got a home. Otherwise, it tends to wander around. You might use it twice. You might not use it at all. Just move it up and associate it with the numerator, and then you're always fine. Now, we need to multiply everything by our LCD. What's our LCD in this case? 10. 2 and 10 are the only denominators we have, so our LCD is 10. So we're going to multiply every term by 10. We're going to have 10 times 3x over 10 plus 10 times 4 equals 10 times negative 5x over 2 minus 10 times 10. So we multiplied every single term by 10. If you've chosen the correct LCD and if you multiply every term by 10, you will not have any fractions left after this step. Does that look okay? Okay, so we multiply. Going to have canceling all over the place. 10 times 3x over 10, 3x, the 10's cancel. 10 times 4, 40 equals. Now, 10 and 2, let's cancel these off. We're left with 5. So 5 times negative 5x is negative 25x. Negative 10 times 10 is minus 100. And then it's a nice simple linear equation. Always will be if you cancel and clear fractions correctly. Well, now we're home free. Let's move the 25 over to the left. Let's subtract 40 from both sides. Sorry about that. No. Yeah, I better, yeah. Okay, 28x equals negative 140. Let's scoot over here to finish that up. 28x. Negative 5. X is negative 5. Be on the lookout. Usually problems that are set up for you in a math book usually work out to be nice numbers. If you start out with nice numbers, they usually end with nice numbers. If you get a really ugly number for one of these problems, double check your work. Okay? Usually when I pick problems to do as examples, except for maybe the first one of each group, which is usually pretty plain, I try and pick problems that have situations that I know cause a lot of mistakes. So in the back of your mind, look at this problem and see, what is it, do you think, what part of this problem do you think that I liked? Or in other words, what is it about this problem that you think causes hang-ups? Could be, but that's usually not too much of a problem. The one on the end, for two reasons. The last term is the one that I chose to look at because the one on the last term there is the one that causes problems. It'll cause problems for two reasons. I'll write that down. Think about there's two reasons that that last term could cause errors. You care to hypothesize on what two things would be problematic back there, Drew? Right. That is a fraction. You can just put it over 1. That's one of the reasons that it's there. It's easy to neglect this when we multiply through by our LCD. That's one reason. Anybody spot the other reason? Yep. You got to be careful distributing that negative sign. Okay? So we'll be careful of both those things. Well, let's get started. First of all, your LCD here is, I won't write it to save space, but your LCD, 3, 5, 6, and ultimately this is over 1. And so your LCD is 30. 30? Yeah, 30. So let's multiply every term by 30. Don't shortcut this. Even though it seems like a basic step, don't just say, well, I'll just remember 30 and distribute, because you won't. Usually. It's too easy to forget. Write it down. It's an important step to not take carelessly. Now, if we've chosen our LCD correctly, we're going to get all kinds of canceling. Aaron, do you have a question?
Yeah, won't you just multiply like the first one, 3x plus 5 over 3 times 10?
Because it's going to cancel and leave you with 10, yep. Right. Okay, so let's go through each term. Each term is going to cancel and leave its own factor in front. So 30 and 3 will cancel. Leaves you with a factor of 10, so we can distribute, and we get 30x plus 50. Next one, 30 and 5 will cancel and leave you with 6. So we have plus 6 times 9x, 54x, minus 12, equals. 30 and 6 will cancel. Leave you with 5. 5 times 6x is 30x plus 50. Now 30 and 1 is really just 30. So be careful. This is where the number one mistake would occur, is on these negative signs. Negative 30 times 3x, negative 90x. That one usually wouldn't cause any trouble. It's the next one. Negative 30 times negative 6 plus 180. Make sure that you associate that subtraction sign that occurred way back here with every term inside the parentheses. That's going to get distributed. And if you get to that point, probably going to be okay. Now we're home free. Now let's combine combine terms. Oh gosh, let's see here. Yeah, let's combine all our terms. On the left side, we've got 84x plus 38 equals, on the right side, we've got negative 60x plus 230. Okay, we'll shuffle our 60x's to the left. Once you got the hang of these, I'm going to do this now to save a little bit of space. You can kind of combine steps here. You can move that 60 to the left and move the 38 to the right all in one step. So I'll just subtract 38. And we're left with 144x equals 192. 144x equals 192. And we're set. Divide by 144. 192 over 144 will, on your calculator, it'll say, what, 1.33333? Here's a case where you don't want to round it off, because no matter where you round it off, you're rounding. Better to leave this as 1 1/3 or 4/3. Those are exact values. Nope. That's a reducible fraction. Either one of those is just fine. We will not take the time to make sure that that's correct, but it is. Okay, if you can do a fractional equation like that, you're in good shape. We're going to come back in a few weeks and see what happens if our variable x is in the denominator. How to work on that, but we need to do some more factoring before we can address that. All right. Okay. Literal equations. The last type of linear equation that's of interest to us is a literal equation. And a literal equation is basically a formula of some kind. It's an equation where, if not all, most of your values are actually variables. But there's only one that you're particularly interested in. Now, we've worked with literal equations before. We started addressing this issue back when we were substituting in units into formulas. We were rearranging formulas a little bit. So we've already addressed this issue to some degree. The thing about a literal equation is, since it's going to have several variables, we have to specify which one we solve. Just like when we were rearranging formulas and substituting in units, we had to say what unit it was or what variable it was that we were after. So, for example, if I put that problem on a test, you saw it in the homework, and say solve it, what do you got to ask? For what? Which one are we solving it for? Let's solve it for x. We could solve it for a n, x, or b. We, of course, are solving for x because it's the toughest one in there. You'd love it if it said solve for B. Get that one right, hopefully. So let's solve it for x. Now there are two paths to go down. What are the two choices that you can use as your first step? Your first step decides which way you're going to go, but you've got two choices here. What are they? You can divide by a. That'd be fine. Then your parentheses dissolve. They're not doing anything after that. Or your other choice? Distribute. Most equations work out better by distributing, so that's what we're going to do. Wouldn't have to, but we will. So distribute, and we get an plus ax equals b. Your answer will look slightly different depending on which method you choose, but they're ultimately equivalent. An plus ax equals b. Now we want to solve for x, so we need to get rid of which term? An has to go. Ax equals b minus an. Yeah, and we're set. We can divide off the a, and x is equal to. We're done. Now it's worth noting that had you gone the other direction, had you decided and divided both sides by a, you'd get a slightly different answer, and I'm going to show you how to manipulate this to see how else the answer could look. Nicole, you had a question? That's a good question. The answer is not yet. You can't cancel out the a's at this point because the a would exist everywhere in the denominator. You've got one term and a is in it, but on the top, a is only in one of the two terms. In order to cancel, it has to be present in every term, and so then you would factor it out and then cancel it. So no, that's a common mistake. Ryan? B minus B over a minus n. Yes, and that's what we're going to do. What you can do is you can say, this is sort of related to what we were doing earlier this week. I forget which day. We can certainly, this is certainly okay. If you leave it there, you're good to go, no problem. But you can recognize that this is the same as split them up and put them over the common denominator, b over a minus an over a. Because then, now if you look at this term, there's an a and it's in every term in the top, in the numerator, and there's an a that's in every term in the denominator. So then, they cancel. See why it's okay here, but not there? All right. Because here, b would be losing an a that didn't exist. And so we end up with, we could also write this answer as b over a minus n, and that would also be okay. Either one of those would be fine. If you would have taken back here and divided both sides by a to begin with, this is the form of the answer you'd get. And you can probably see it. Divide by a, the only step you'd have left would be subtract the n, and you'd be right here. Okay, last problem of the day right here. Well, I'll run the marker. You tell me what to do. I mean, telling me what to do is related to the math problem here. Distribute the p through. Your LCD is p, so we're going to multiply everything by p. Cleared the fractions. Good. Now there's no fractions left. That's got to make you smile. Distribute. KB plus 2 KNP. That's equal to 4 KNP. Now these happen to be the same, but what if it was 2NKP or 2PNK? Would that make it a different type of term? No, the order of multiplication does not matter. So as long as these are being multiplied together, we can put them in any order. 2 times 3 is the same as 3 times 2. Okay, well now, I forgot which one are we trying to solve for? N. So let's collect the n terms together. Let's put them over here. To KNP. And so, divide off your 2kp. How's that look? It's almost good. It's a reducible fraction, though. Your k's cancel off, powers of exponents. And so n is actually equal to b over 2p. N is equal to b over 2p.